All right, so now we're going to talk about long division. And you've already seen long division way back in elementary school, I'm sure, but we're going to go ahead and refresh our memory. Remember 525 divided by 5, one of these types of problems. You plug that into your, well, you shouldn't have to plug that into your calculator, but let's go ahead and run through this. 525 divided by 5 can be rewritten like this. And so you go, how many times does 5 go into 5? Well, you'd say, okay, well, clearly that's once. And so then you come down here. 1 times 5 is -5. And so in the hundreds place, right? So that's 0. 2 comes down. And 5 does not go into 2 at all. So you'd say 0. Then the 5 comes down. 5 goes into 25 5 times, giving you a remainder of 0. So the answer here is 105. So you come over here and write 105. Right? Simple long division. So as we can already see here, this divides with no remainder. With rational polynomials, the places will be replaced with terms. So we had hundreds, tens in first place, but the ones place is replaced by the constant term. The tens place is replaced by the first power term. So that would be so the constant, as a reminder, that's x to the 0th. This would be x to the 1st. And then the hundredth place is replaced by the second term, or the x squared term. And we'll be looking at the coefficients in front of each term. So like we did for 525 divided by 5, let's look at x squared plus 8x plus 16 divided by x plus 4. Note, in the hundredth place, or what would have been the hundredth place, right, that we've got a 1, and the tens place is an 8, and then in the ones place we have 16. So important thing to note is we just the bottom goes here, the top goes inside, just like it did before. All right, so how many times does x, we're just looking at the first term here, go into x squared? And the answer to that, of course, is x, right? X times x is x squared. And so then we come down here, x times x is x squared plus 4 times x. Do not forget to multiply the second term. And then we subtract that through. 8x minus 4x is 4x. Drop the next term, and we got 4x plus 16. X goes into 4x, a grand total of 4 times. And so x times 4, that's 4x. And then 4 times 4, that is 16, giving us a remainder of 0. So x squared plus 8x plus 16 divided by x plus 4 equals x plus 4. Or I guess I left a spot for me to write it right there. And note that the top is x plus 4 squared, so it should make sense that when you divide x plus 4 squared by x plus 4, the result is simply x plus 4. All right, so next page, we want to reduce the next expression, and just like we did before. So we would write 2x plus 3 divides into 4x squared plus 12x plus 9. All right, so 2x goes into 4x, a grand total of 2x times. 2x times 2x is 4x squared, so we got 4x squared. Don't forget to multiply the 3, so we've got plus 6x giving us this. And the result is 6x, right? This is 0. 12x minus 6x is, of course, 6x. The 9 drops down. And now we're looking at how many times does 2x go into 6x. And, of course, 2x times 3 is 6x, so we would write 3 right there. 2x times 3, 6x. 3 times 3 is 9. So we will have a remainder of 0. So the answer to this, when you divide these two together, will be 2x plus 3. Okay, that's what that reduces to. All right, so the next example, we're going to actually be graphing this. So note that after we're done dividing through, we will have a discontinuity of x equals 2 being generated in the bottom. But first, let's do our long division. So we've got x minus 2 divided into x squared minus 4x plus 4. All right, so x goes into x, a grand total of x times, because x times x is x squared. So we get x squared minus 2x. And here we have negative 4x minus negative 2x. So minus negative 2x turns this into a plus 2x. So negative 4x plus 2x is negative 2x. The 4 drops down. And x, so now we do the next line. X goes into this term here, negative 2x. Negative 2 times negative 2 times x gets us this here. So we would write minus 2. So negative 2 times x, negative 2x, negative 2 times negative 2, that is positive 4. So we got a remainder of 0. So we can rewrite this guy as x minus 2 such that x does not equal 2. And so the graph is just a straight line with a slope of 1, and we're going to pluck the 2 right out. So straight line, slope of 1, y-intercept of negative 2. Right, goes through here, open circle there, and solid circle everywhere else, of course. And that is our graph. All right, so going back to the elementary school example, 681 divided by 6. So we would go through it the normal way. 1 right there, because 6 times 1 is 6. So there's our 6, 0. The 8 comes down, and that goes in another 1 time. 1 times 6, that's 6. Subtract, giving us 2. 1 comes in. And then when we get to 6 and 21, so 6 times 3 is 18. That's the closest we can get. So subtract 18 out from there. But, we've got a 3. So this is 113, remainder 3. So how can we rewrite this? We can rewrite it as 113 plus 3 divided by 6. Note it's the remainder divided by the old denominator. And of course, we can rewrite this as 113.5. Okay. So, important thing to take away from the above example is that we express the remainder as a fraction. So you do when you have the dividend divided by the divisor, right? The divisor goes here, dividend goes here. You've got your quotient which is, just the result of doing the division, and then a remainder. And so you just rewrite everything like this right here. The quotient plus the remainder over the old divisor. So now we're going to use long division to expand the following rational polynomials. So we've got x minus 1 being divided into 3x squared plus 12x plus 9. So now we run through the long division. X goes into 3x squared, 3x times, right? 3x times x is 3x squared. So we write 3x squared minus 3x. And I always like to do the minus with the parentheses out there just so I don't get confused with what's a negative and what's a positive. So 3x squared minus 3x squared, that's of course 0. 12x minus negative 3x minus the negative makes this a positive, so we've got 15x, and then we add the 9 right there. And so now we're left with 15x, and so how many times does this x here go into 15x? Well, of course, it is a grand total of 15 times. Right, so x times 15, that's 15x. 15 times negative 1, that's negative 15. (15x minus 15x, 0, 9 minus negative 15. Remember, the minus negative makes that a positive, so that gives us 24. And so don't forget to write that as a remainder right there, remainder 24, because we ran out of x's to work with. So now we simply rewrite this right here, 3x plus 15 with a remainder of 24. So write plus 24 divided by the old divisor of x minus 1. And that is how that one reduces. So moving forward, we've got this whole thing divided by x minus 1 yet again. So we write x minus 1 divided by x cubed plus 2x squared plus 2x plus 1. So x goes into x cubed, x squared times, so x times x squared. Of course, that is x cubed. Don't forget to do both of these. So minus x squared, 2x minus negative x squared. So this becomes a positive. So we've got 3x squared right there. Don't forget to drop the next term down, 2x. So now we're left with how many times does this x go into 3x squared? What goes into it? 3x times. So we've got 3x squared minus 3x. And so we've got, of course, these guys go away. 2x minus negative makes that a positive. And so we're left with 5x. Drop the next one down. Okay, so now this x goes into here 5 times, so plus 5. And so we've got 5x minus 5. And again, we are subtracting that whole thing. Negative minus a negative makes this a positive, so 1 plus 5 is 6. And so we've got our remainder of 6 right here. And so our final answer becomes x squared plus 3x plus 5 plus 6 over x minus 1. And that is the final answer. Next one. Now we have a little more interesting term in the bottom, x squared plus 1, but the concept still remains the same. So we've got x squared plus 1 divided into x cubed plus x squared plus x plus 1. All right, so x squared goes into x cubed, a grand total of x times x squared times x, that is x cubed. And then we've got our plus x. And note how I'm not putting it directly under the x squared. I'm putting it under the term that it matches. So here we are. These two terms go away. And so I've got an x squared. Going to drop that 1 down. And note that this goes into our term, a grand total of once. And so I've got x squared plus 1, 0. So we've got a remainder of 0. So it's simply x plus 1. And note that I don't really need to write a such that right here, because the only way I'm dividing by 0 is if I journey into the imaginary number world. So this will be fine enough for right now, but if you wanted to be complete, you could write it like this, such that x does not equal positive or negative I. But if you're not dealing with complex numbers anyways, it's completely unnecessary. All right, so moving on to the next one. A little bit longer polynomial on the top, but that is not a problem. The principles remain the same. And again, make sure you're pausing the video and trying to solve these on your own, and then see if you get the same results as what I am getting. That is how you get the best results. All right, so here I do x cubed because x times x cubed is x to the 4th. So x to the 4th, 1 times x cubed, so that becomes plus x cubed. And so all that's left is a single x cubed. Bring the next one down, plus x squared. X squared times x is x cubed, so write plus x squared. So x cubed plus x squared. So far, this is working out pretty nice. And so we drop the next 2 so that we have enough terms to work with here. X plus 5, so x goes into x, a grand total of once. And so I got x plus 1. So we have a remainder of 4. So our result will be x cubed plus x squared plus 1 with our remainder, so that would be plus 4 divided by x plus 1. And that is our answer right there. All right, so now we're going to talk a little bit about slanted and curved asymptotes. We're going to use the remainder, which can be written as a fraction, and can help us identify slanted and curved asymptotes. So whenever we go through our division, we have y equals the dividend over the divisor, of course. And when we perform this division, we've got a quotient plus the remainder over a divisor. So the curved slanted asymptote will have the equation y is the equation of the asymptote here is the quotient. That is what we have right there. And any vertical asymptotes are found by setting the divisor to 0. So a really important thing to note that is if the remainder happens to be 0, then there will be no curved asymptotes. Okay, so let's go ahead and work with what we got here. Graph the following functions and their asymptotes. So we know there will be, well, there could be a discontinuity. There's going to be a discontinuity at -1. We don't know if it's going to be a removable or if it's going to be vertical. So let's go through our division here. So x plus 1 divided by x squared minus x plus 1. And so multiplying through, right, x, that way we got x squared plus x. Keep in mind we're minus, not subtracting that, so it becomes negative 2x. Add the 1 right there. And then here, negative 2. So we get negative 2x minus 2. So 1 minus negative 2 minus negative 2 becomes positive 2, so it's the remainder of 3. So this becomes x minus 2 plus 3 over x plus 1. So we do have a horizontal asymptote right there at x equals 1. And then we also have this curved asymptote, or a diagonal asymptote, if you will. And it'll simply be the straight line going through here, and it's got a slope of 1. Like so. So now we got the asymptotes, let's figure out a point here. So we can easily find the y-intercept by setting x equal to 0. We'll do that for this first equation. We have 1 divided by 1. And so clearly we've got a y-intercept here of 1. So that is a good point. That tells us we're above the asymptote here. I just realized I graphed at positive 1. Let's go ahead and put there we go. Ignore that. My apologies. All right. And so our graph comes through, hits here. It goes up there. And because this is a discontinuity of order 1, we change sides, so it'll be down here. And there we have. So we've got our vertical discontinuity here, our diagonal discontinuity here. Because we had a y-intercept there, we know we're above this line at this point. So we graph that, change sides, and we get that side there. That is how we graph that part right there. So moving forward. Do a little long division here. We got x cubed minus x plus 1, so this goes into there. X squared times x cubed plus x squared, so we subtract that through. X cubed minus x cubed is 0, negative x squared, and then this minus x comes down, and so x goes into negative x squared, a grand total of negative x times, so giving us negative x squared minus x. Subtracting all that through is 0. The 1 comes down, that goes through, grand total of 0 times, so we've got a remainder of 1. And so our equation becomes x squared minus x. And of course, we've got our remainder of 1. So plus 1 over x plus 1. So let's look at this quotient, right? The curved asymptote. So we'll say YC for curved asymptote. CA, let's do CA, there we go, is x squared minus x, which is the same as x times x minus 1. So we know that our curved asymptote goes through the points 0 and positive 1. And let's go ahead and find the coordinates of the vertex for this guy. So we got h naught over negative b divided by 2a, negative b. Right, that's the number in front of the x. So negative 1 divided by 2 times 1. And so this is simply 1/2. And now to find the y coordinate, we just plug that into the equation. We're going to use this form because it's going to be a little bit easier to work with. So we've got 1/2 times 1/2 minus 1. 1/2 minus 1, negative 1/2, and then multiply it by 1/2 again to get a negative quarter. So that'll be our vertex about right there. So go right 1, up 1, left 1, up 1. There we go. It looks something like that. We got our general shape. And then don't forget we've got this at -2. Right there. Of course, those will meet up in the corner of the page. Let's find the y-intercept real fast. Y-intercept, of course, that is f of 0. And for our problem, that is like 0, 0, 0, so 1 over 1. There we are. Putting us above the curved asymptote, so it'll go up with it like this. And as we move right, it'll start getting closer and closer. And then on the other side, of course, we're below. And it'll look something like that. All right, moving on. So now we're going to use long division again on this guy. So we got 0.5x. Q, just go ahead and fill everything out. All right, so here this is 0.5x squared plus 0.5x squared, so subtracting through. So we got negative 0.5x squared minus 0.5x. And so keep going with it. So that all goes away quite nicely, leaving us with a remainder of 1. So we can rewrite this guy as 0.5x squared minus 0.5 times x plus 1 over x plus 1. All right, and so let's look at the equation of the asymptote. Note that the asymptote is going to be parabolic in shape, and so we've got 0.5 times x squared minus 0.5. And that's the same as 1/2 times x times x minus 1. And so our asymptote, our curved asymptote, will have coordinates of 0 and positive 1. And it's going to be smooshed by a factor of 1/2. It should be pretty clear that by symmetry, that the x value of the vertex will be 1/2. So we'll plug that in, and we'll actually get to be 1/8 is where we should be right here. And so it'll be something like that. I'm just going to go and sketch it without plugging in any points, just to kind of get us moving along. And then we've got our vertical asymptote right there at a 1. So plugging everything. Well, first let's find the y-intercept, which is f of 0, which will be just 1, right? Because 0, 0, 0, 1 over 1. And so there is our intercept there. And so as we get further to the left, we'll be getting closer to our parabola, but then it'll kind of diverge as we get closer to this discontinuity, and the same on the right. Okay. Moving forward. So here we want to note that if the remainder is 0, then the x value is a root. In general, r equals 0 implies that dividend divided by the divisor is the quotient, right? Because there's no longer a remainder involved in it. And so taking this equation, we can rewrite this by dividing the divisor by both sides to show that the dividend equals the quotient multiplied by the divisor. So let's put this into action. Consider this polynomial right here, which has a root of x naught equals -1. So because it is x equals -1, we're going to divide through by the polynomial x plus 1. So let's go ahead and set this up. X to the fourth plus 2x cubed plus 2x squared plus 2x plus 1 divided by x plus 1. That's what we're doing, yes. All right, so x cubed. I'm going to go through this a little bit more quickly since we should be getting this pattern down. And then for the last one, of course, 1 minus x plus 1. And of course, our remainder is 0. So this simply becomes x cubed plus x squared plus x plus 1. But we can, as per this, right, multiply both sides by x plus 1. And you will see that x to the fourth plus 2x cubed plus 2x squared plus 2x plus 1 can be rewritten as x cubed plus x squared plus x plus 1 multiplied by x plus 1. Note that this helps us to factor the x plus 1 out of the original polynomial. So that's how we're going to be using this. All right, so I'm going to let you guys do this again, but this is divisible by x plus 1. I would encourage you guys to, on your own, divide that by x plus 1 and see where that takes you. All right, so let's find the remaining roots of the given polynomial and rewrite the polynomial in factored form. So we're going to take this one all the way, and we're given that x equals 1 is a root. So what do? We take this guy, divide it by x minus 1, because x positive 1 is the root. All right, so now we just perform the long division. Again, multiply the second term. Do not forget that. And we know the remainder is going to be 0 because we're given that x not equals 1 is a root. Okay, so our polynomial is x squared plus 4 multiplied by x minus 1. If I multiply these two guys together, I'll get this original statement back. Note that I can break this down further because this is a sum of squares, right? X squared plus 4 can be rewritten as x plus 2i times x minus 2i. Refer back to our earlier handout where we discussed this. And so a fully factored will look like this: x plus 2i times x minus 2i times x minus 1. And that is the fully factored form of our polynomial.